At this time, we will hear from our second graduate speaker, Sarah Ajayi. Sarah was born in Dallas, Texas, but grew up in Nigeria. Her Bachelor of Science is in Crop Science from Benson Idahosa University. She returned to United States to get her Master's in Plant Science at West Texas A&M University. Sarah is currently pursuing a Ph.D. in Agronomy at Texas A&M University, and she was awarded with Cole's Excellence Fellowship for her Ph.D. degree. Her goal is to contribute in a sustainable crop production under various agro-climatic conditions and stresses with the help of recent techniques. Her research interest is on developing relatively simple, inexpensive, but rapid selection tools that plant breeders can utilize to screen huge number of genotypes in a relatively short time. Everyone, please welcome Sarah Ajayi.
Thank you, Smith, for the introduction. I would like to first and foremost thank the organizing committee for giving me the opportunity to make my presentation. The title of my presentation is Spectral Vegetation Indices for Estimating Growth of Winter Wheat Genotypes. And it's no longer news about the fast-growing population, which is about 7 billion, and estimated by the year 2050 to reach about 10.7 billion. And we know with that fast-growing population also comes the growing food demand. Also, we know wheat is one of the most important staple cereal crop, and the wheat demand in year 2010 was estimated to be like 666 million metric tons, and by the year 2050 is like estimated to be like 880 million metric tons. That brings about the need for wheat breeding, and wheat breeding as a factor of achieving self-sufficiency and self-sustainability. Self-sustainability in the sense of being able to provide enough food to meet the growing demand and also to manage environmental issues such as drought. The process of monitoring the growth and performance of wheat genotypes for better yield under various agro-climatic conditions and stresses can be labor intensive. You can imagine if wheat breeders definitely have hundreds to thousands of plots. So you can imagine me taking a leaf area index on each of the plots. It takes a lot of time. But with remote sensing methods, I will highlight that basically one of the best of it is being able to take simultaneous measurements and also as an automated approach to identify the best plant variety of interest. So looking at this figure, the basis of remote sensing essentially is that different materials absorb and reflect radiation differently. So looking at this figure, we see that incident solar radiation descending on grass, descending on water, descending on bare soil, definitely will show different reflected solar radiation back to the sensor, back to the satellite. So with that, we can say we can differentiate targets based on the their spectral signatures. The electromagnetic spectrum has the visible, near-infrared, shortwave infrared. The visible region has the blue, green, and red wavelengths, and we know the blue and red wavelengths. Actually, the visible region is from 0.4 to 0.7 micrometers, as you can see here. Then the blue and red wavelengths, they absorb more radiation compared to the green wavelengths, and that's due to the leaf pigmentation in the plant. Then the near-infrared region, which is from 0.7 to about 1.4 micrometers, reflects more radiation based on the cellular structures of the plant. And also the shortwave infrared region, which is like from 1.4 to 2.6 micrometers, has about, we see at different wavelengths, we see absorption and radiation of, reflection of radiation. That's due to the water content in the plant. So with these controlling factors, the wavelengths and the spectral information they provide, you can put them into mathematical formulas known as vegetation indexes. The vegetation indices may have some relationship to the amount of vegetation and its characteristics in a given image pixel. So some examples are the normalized difference vegetation index, which is used to map vegetation, the normalized difference water index, which is used to measure water content, then the soil adjusted vegetation index, which is used to measure soil brightness when the vegetation is low. Among all these vegetation indices, the perpendicular vegetation index accounts for bare soil. The perpendicular vegetation index uses brightness values in the near-infrared band and red band to measure the perpendicular distance from the vegetation spots to the bare soil. That's in a near-infrared red scatter plot. And that's also where we get the intercept and slope values. Now let's look at this first figure here. We have on the y-axis brightness values in the near-infrared band, and on the x-axis we have brightness values in the red band. Now looking at the vegetation pixels, we know definitely vegetation pixels have higher near-infrared brightness values, and they have lower red brightness values. That is below the underlying soil. So the next figure is the same type of graph, but using Landsat bands. We see that as the vegetation density increases, the vegetation pixel, the vegetation spot moves towards the top left corner of the graph. That's away from the soil pixels. Lastly, it's same figure, but differently. Now, looking at this, we can highlight the bare soil line based on the best fit line around the soil pixel. So that's why we have that line, that's the bare soil line. And also we can highlight where the full canopy is. So based on this plot, based on this graph, we can try estimate ground cover based on the PVI of a plot divided by the PVI of the full canopy. So I'll just go quickly to the objective of this study is simply to evaluate genetic variability in growth and performance of 20 wheat genotypes under 2 water regimes as rain-fed and irrigated using spectral vegetation indices estimated from aerial imagery, from green seeker sensor, and also from percentage ground cover estimated from digital photos. So this study was carried out in Bushland, Texas, used randomized complete block design with 3 replications. The growing season was last growing season actually. So the aerial photographs, aerial imagery was actually taken with a manned aircraft, basically. Digital photograph just using a digital camera just to try and measure ground cover. Then also the green seeker sensor used to measure normalized difference vegetation index. So for the aerial imagery, we use the Tetra mini multiple camera array, which has spectral range from, that's the wavelengths from 450 to 1000 nanometers, and the spatial resolution, that's like the number of pixels in an image. Now I want to talk about the spectral resolution, which also like the wavelengths. So per each frame, we have like 12 bands. That's like giving like 12 different images to work with per frame. So we have a picture of the manned aircraft and the camera that was used. Let's go right into some results and discussion. On this figure, we have aerial images of the rain-fed and irrigated fields. So on my first column, I have the rain-fed fields, and on the second column, I have the irrigated fields. While on the first row, I have the first stage after emergence stage. The second row, I have the tillering stage. And the last row, I have the late jointing stage. So this type of, the outline will be followed in the next 4 slides. So just take note. Then remember I have 20 wheat genotypes replicated 3 times. That gives me 60 plots. So based just for this study, I worked on 60 plots, even though the breeders are interested in the old field that you can see here. It's really where this, the 60 plots were highlighted from. So just looking at the 60 plots, you can see some redness. This is displayed in color infrared, meaning redness show more vegetation, and we can see some spots that are scanty. So we see some variation there, but let's do some analysis and see what we come out with. Oops. First, we started calculating normalized difference water index using the near-infrared band and a water band that is that around 900 nanometers in place of shortwave infrared band. So I'm able to come up with the NDWI max. So this is the same layout like I said before. Then I have highlighted my 60 plots, that's with 20 wheat genotypes. Just looking at them visually, we can see maybe under the rain-fed condition, that's the first column, not really significant differences, but under the irrigated condition, we see some significant differences. So I'm going to show some tables with my 20 wheat genotypes. We can pinpoint, well, definitely no significant difference at the first, that's after emergence stage. Let's look at the tillering stage. Okay, no significant difference, but under irrigated fields, we see significant differences. So I can pinpoint that I have 10 Texas A&M genotypes, and the other 10 are from, some are from Kansas, Colorado, Oklahoma. We can see that some of the term genotypes show more water content. So I've got to mention that in the map, we have the blue colors show less water content, the yellow/red colors indicate more water content. So the last stage is the late jointing stage. Also no significant difference under rain-fed fields, but under irrigated fields, we see we can pinpoint which genotypes show more water content compared to the others. Next up is the normalized difference vegetation index calculated using the near-infrared band and the green band. Coming up with this map, I also have highlighted my 20 genotypes. So let me look at the table. We can see it visually. We can see there are some significant differences in some of the plots. But looking at the table, I have the first table is after emergence stage. No significant differences under both fields. But at tillering stage, we can pinpoint that like some term genotypes show densiest vegetation canopy compared to the others. So again, the red colors indicate bare soil. The densest vegetation is shown by the green colors that's on the map. Now the last stage, we see significant differences for both fields. That's, we can pinpoint which of the genotypes show the densest canopy, vegetation canopy compared to the others. Now next up, I'm going to show the near-infrared scatter plots, as we already see, which was used to calculate the perpendicular vegetation index. So here we have the plots. Remember, we have on the y-axis brightness values from the near-infrared band. On the x-axis, we have brightness values for the red band. So looking at this, we can see for each stage, remember the first row is after emergence stage, second row tillering stage, third row late jointing stage. We can see as the growing season progresses, we see that the pixels, the vegetation spots shifts towards the top left corner of each of the plots, away from the soil pixels. Then with that, we can align our best soil line based on the best fit line around the soil pixels. Then also I have highlighted my 20 weed genotypes, that's the pixels, see where they're located, and also we can also pinpoint where the full canopy is. So with that, I can try estimate the ground cover based on the PVI of each plot divided by the PVI of the full canopy. Then I'm able to come up with the percentage ground cover map. Next up, I'm highlighting my 20 weed genotypes also here. We can see at all stages and at all fields we have significant difference except after emergence under irrigated fields. And I think visually we can see that I don't see the significant differences there. Okay, let's see the tables. We can pinpoint which of the genotypes indicates more densiest vegetation canopy compared to the others. Then next, the first table is after emergence, don't forget. Then the second table is at tillering stage. We see significant differences in both fields. We can pinpoint which of the genotypes also indicated densiest vegetation canopy compared to the others. Then the last was the late jointing stage. We see significant differences among the wheat genotypes, and we know which one shows more densiest vegetation canopy compared to the others. Next, I'm going to show some relationship. It seems it's flipped up a bit, but I'm going to highlight the first table is the rain-fed fields. The second table is the irrigated field. So I'm going to just highlight that for the rain-fed fields, we see 66% of variability explained, 66% of variability in the percentage ground cover obtained from the digital photos is explained by variability in the percentage ground cover obtained from the perpendicular vegetation index. Compared to under irrigated condition, I think the good relationship that for irrigated condition is 79%. Also looking at the NDVI relationship between the one collected from the green seeker and also the one obtained from the aerial images, we can see for irrigated we find 87% explained, but for rain-fed we see poor relationship, and I would say that is due to poor stand on each of the plots, and definitely on the field when we are capturing it using the green seeker, we'll look for the representative point on the each plot. But compared to the aerial images where we have fewer pixels to work with, so that's why we have poor relationship. Looking at that's the percentage ground cover under rain-fed condition and NDVI also. But mostly we see good relationship. That's a good point. In conclusion, term genotypes were mostly similar, while other genotypes showed more genotypic variations due to the wide genetic background, especially during at tillering and late jointing stages. Significant relationships provide the possibility of using the estimated parameters as an indirect tool to screen large numbers of wheat genotypes. So we look ahead to repeating the study with more consistent field data collection and at specific growth stages. And also all things being equal, we get yield data. We couldn't get yield data last season because of hail, some damage. At this moment, I'd like to thank my committee members, Dr. Sher, Dr. Ibrahim, Dr. Rijan, Dr. Rod, Dr. Liu, and Dr. Sher, Texas A&M AgriLive Research, Amarillo, Texas, iPlane Consulting Firm, and my project sponsors. Thank you very much.
Thank you, Sarah, for your presentation. We now have a time for one or two questions.
Thanks for the interesting talk. I was curious that there seem to be relatively few significant differences in most of the stages, and I'm wondering why you think that was.
That's like from moving from one stage to another?
Within any one of the stages, there seem to be very few significant differences among the genotypes.
Yeah, because, okay, actually, most of we have 10 of the genotypes are quite similar, like most 10 of them, so you can expect mostly similar. So the only 10 are like the ones coming from Kansas, Colorado, Oklahoma, they are kind of like they have wide genotypic background compared to the term genotype. So since they are mostly similar, that means we have little or or no differences among them at each stages.
Any more questions? Thank you, Sarah.
Thank you.